Your self-designed mobile ham radio antenna for field purposes or traveling. But come on, really? Is that all we need? Come on, let's find out. Hi and welcome to TRX Bench. Well, recently I have been asked if it is possible to build an easy antenna for field purposes or for traveling. So that means, can I build an antenna for any band and also for VHF bands to be able to take it with me on a traveling or if we have a field day. So an easy antenna which can be used to put it into a tree and can be operated wherever you are, and I can design it and construct it in an easy way. And that is what we want to look into, and therefore we try to build such an antenna, and we want to go through all the designing questions, and of course for all of you who only want to build it, we give some informations without any mass or anything. So just and easily what you have to do to get a working antenna. But for all of you who really want to go all through the mass to be able to do these antennas for any band you like, we will do that as well. So welcome and follow me along on this journey. What we really want to look into today is a so known Fox antenna from Josef Fuchs, who is an Austrian radio amateur, or was an Austrian radio amateur in 1927, I believe. And he designed and developed this kind of long wire antenna. And the special is that it is a long wire antenna which is exactly half lambda, or it is lambda, or it is 3/2 lambda. So we have these three variants where we can play with, and we will play today with the half lambda version, and you really can construct any band you need with this kind of, and it is a kind of vertical antenna. And the beauty is you really can put it when you have it together, you can really put it this way and carry it around wherever you want to go, and then you simply fold it out, and you can hang it into a tree or whatever you like. And yeah, so the only thing you need is a piece of wire, and you need a little capacitor, and we need to wind a coil, and that is what it is all about. And as it is a long wire version, we feed our signal into one end, and you may already know that the problem always is, if you want to feed HF signal to the end of our antenna, we have to fight a very high impedance. So the impedance at the end of such long wire antennas are 2 kilo ohm up to 2.5 kilo ohm, and we all know that the input of our radio transceivers is around 50 ohm. So we cannot really connect the end of such an antenna directly to our coax connector, because simply we would have a mismatch, and therefore we need a little trick to convert here our high impedance to 50 ohm. And when we look here onto Wikipedia, there we find something about this Fuchs or Fox antennas, and the most important diagram is this one here, and there we really get all the important informations. First of all, we have here our wire, which we have taken this wire for, and then you see a little tank circuit, right, which is connected finally to an antenna cable, right? So what we need is to look into this here, that we really will be able to transform at least our, and you see it here. So here we have the assumption of 2.2 kilo ohm, which is the impedance at the end of the wire. And normally, if we would work with a dipole, we would feed right into the middle. And right into the middle, if we do everything right, we will have more or less 50 ohm. It depends on some little tricks, okay, but basically we feed a dipole right in the middle, and then it is different. But when we feed it at the end, all is completely different, and therefore we really need to manage here our high impedance. Well, the problem or the challenge now is to get here the right dimensions to get all right, and that is what we want to look into. And of course, for all of you who do not want to do all the math and all the calculations, we will give you, especially for our CB radio friends who are working on 11 meters. So we will give all the needed informations about this tank circuit, how to wind here our coil, and what capacitor we need to take, and how we get the transformation from 2.5 or 2.2 kilo ohm down to 50 ohm, which is our known impedance on our radios, right? But first of all, let's start how we can go step by step, that we really could do it for any antenna and for any band, any frequency we want. All right, and the first thing we have to talk about is about lambda. And lambda is the wavelength. And that is very important because we know that we are working on different bands. So 80 meter, 20 meter, I don't know, 40 meter, 10 meter, 11 meter, and in the VHF area 2 meter. And there you already can hear that there must be a difference between the frequencies we are working on. And when we're talking about our radio frequencies, we already use both. So we are talking about the band and we are talking about the frequency. So I've put down here for explanation some of our used bands in ham radio. And yeah, so we already know 20 meter is our 14 megahertz area, right? Or 40 meter is our 7 megahertz area, or 160 meter is our 1.6 megahertz area. And so you see the band and the frequency has a relation to each other, And that simply means when we're talking about 14 megahertz, which is the 20 meter band, then the 20 meter is already telling us that we are talking about a wavelength of 20 meter, right? And there we have already the information which antenna length we need, because our antenna length needs always a relation to the meter band or the frequency we are working on. So that hangs together, and if we are talking about a resonant antenna, then we really need to take the meter band, the frequency, into our consideration to get a real and good working antenna. Well, and if we have, for instance, a frequency where we do not know directly, automatically, the wavelengths, so the meters we are talking about, then we can calculate it, right? So I want to show how it works, and once again, so we do both. We show how we can calculate it, and of course at the end, especially for 11 meter, I will show you the figures so that you do not need to go to all this mass. Right, so our formula for wavelengths is lambda is equal c over f, and c is the speed of light, and f is our frequency. So what you need to know is the speed of light and the frequency which is in question to get our lambda. And as I already told you, you need the lambda to know how long your antenna needs to be. Okay? Right, and here are our figures which we want to calculate. And what we see here for c, our speed of light, we have a constant of 3 times 10 exponent 8 meter over seconds divided by the frequency we want to know our band or wavelengths, right? So I've chosen here in the 2 meter band the 149 megahertz. So that is simply because I have been asked by some of our freenet radio amateurs, right, which are working on freenet, so that is a 2 meter freenet frequency, which is given free here from the authority. So we have, what is it, 6 channels, I believe, where everybody can work on without having a license. So that is 2 meter freenet. And that is in the 149 megahertz area. And because I have asked from some of those guys, I will use this 149 megahertz to demonstrate it on this. But anyways, it will work with any other band in exactly the same manner. So if we would like to find for 14 megahertz the wavelengths, then you would put here, instead of 149, you would put 14 megahertz. So that is all. And for all of you who are still looking for a good calculator, I can really recommend this Casio FX82DE Plus, because it is a calculator where you can directly put the formula in its form into our calculator. So you see I have here put in 3 times 10 exponent 8 divided by 149 10 exponent 6, which is our megahertz. And now when I press here my equal button, then we get, and there you can read it, it is equal with 2.01 meter. And the 2.01 or the 2 meter so is indicating what we already know before. I mean 149 megahertz is the 2 meter band, right? And the only thing what this is showing here is that we are right when we are talking about 2 meter band, because wavelengths of our 149 or 145 megahertz is 2 meter. That simple it is. Okay, and since we know that it is 2 meter, what we have been already known before, but anyways, now you can calculate the wavelengths for any frequency you need it. It is always the same. Okay, so now where we know it is 2 meter, we really can go ahead, because we have talking about half wave lengths, right? So we will work with antenna which is a half wave design, and therefore if we have here a 2 meter and we are talking about lambda half, right? So that is what it is. It is half lambda, or lambda over 2, which is the same. And that means that our antenna, always considering that we are talking about half wave, right? And that simply means our wavelengths divided by 2, and that is what it is. And that means the design we are talking about is 1 meter. So our antenna needs to be 1 meter for 149 megahertz in the 2 meter band. That is what we have talking about. Okay, so let's go back for 1 second to this picture. So we know now that here our antenna, so that is our piece of wire, needs to be 1 meter, and it needs to be a little bit more, but that is what we want to talk later on. Now it is important to think here about this tank circuit. So that is a resonant tank circuit which will be or has to be resonant on 149 megahertz. So this design here, and that is what we need to design right now, that for our 149 megahertz this tank circuit will be resonant, because otherwise it will not work. And then secondly we have to think about our 1.2 or 1.5 kilo ohm Z, which we have here at the end. So it's a long wire end, which we need to transform into 50 ohms. So that is what we need to think after we have here our right tank circuit. Okay. And that already means that we can think about our antenna design, how it needs to be when we have built it. And what we know already is that the piece of wire which we need for our antenna is such an electric wire, so simple for mains distribution, which is used in any house, right? And we need a little capacitor, which is this one, and we need a coil, and here we have the coil, and therefore we need this silver wire. So the difference is, for the VHF band we use this silver wire, because we really have to deal with very, very low inductors, and therefore this is what we need. If we talk about, you know, our shortwave band, then we would use a core here, and would simply use copper wire, which is very nice for shortwave designs, but especially here for our VHF design, right? It is really easy and good to use this silver wire. Right, question now is how we can go ahead. I mean, we know that this tank circuit needs to be resonant, and we know it needs to be resonant on 149 megahertz, and that means that this both components needs to be together resonant for the wanted frequency. And how can we achieve this goal? And that goal can be achieved with the Thomson equation, and that is what I've written down here. So our wanted frequency of 149 megahertz is equal to 1 over 2 pi square root out LC. Okay, I agree. So in this form we can't really use it because we are looking for L or C, because we have already our needed F, which is our 149 megahertz. So we are not interested in the frequency, we are more interested on either the L or the C. So that is much more what we really need. Alright, so for our purposes it is always a good idea to start with our L, right? And we have to change here our equation to L, right? So we just build it over to L. And if we take this formula and convert it to L, then we have L is equal 1 over C in brackets 2 pi F squared, right? So that is how we get out our L. And we are using a little assumption, or well, that is experience over the years for our C, which we do not have as well for the moment in time, but we can make the assumption that for HF we start with 50 picofarad, and the C for VHF we start with 5 picofarad, and that is what we want to do. So this C here will be equal to 5 picofarad. So therefore now we have all we need to get here a value for our L1. Right, and now it is simply to put these figures here into our calculator, and I just do it here online. So we set 5 picofarad, and 5 is 10 exponent minus 12, which represents our picofarad, right? Then we open the bracket here, and we have 2 pi, which we have here, and we know that we have 149 megahertz, which is exponent 6. Now we close our bracket and we square it, and then we can say what is the outcome, and therefore we press here our equal button, and now we have minus 7, 10 exponent minus 7, which is not an engineer form, so therefore we use here our engineer button, and now it is converted into a term which is better known in the engineer's world. So now we have nano, right? 10 exponent minus 9 is nano, and that means our outcome is 228 nanofarad. Sorry, wrong. We are looking for L, so that means 228 nanohenry. Okay, 228 nanohenry. So that is the coil we need for our 149 megahertz. And you already see that 228 nanohenry is really a very, very low inductance. Yeah, and you can find it in this both terms, so 228 nanohenry, or what you can find as well is 228 times 10 exponent minus 9 Henry, which is the same, which is totally the same. And once again, we used for our assumption our 5 PIV, right? So that is important to know. So for HF and for VHF, because simply we need to start somewhere, okay? But before we go now ahead to build and first to calculate our 228 nanohenry coil, we need to do a little addition here to our little circuit, because remember, we know that we have here 2.5 kilo ohm. So that is what we discussed earlier, right? That is 2.5 kilo ohm. Okay, it is between 2 and 2.5, so it always depends a little bit. But again, we need to start somewhere, and I have chosen here 2.5 kilo ohm to start. And now you may remember we cannot connect 2.5 kilo ohm directly to our radio antenna socket, because it is 50 ohm. So that means we need to convert our 2.5 kilo ohm back or down to 50 ohm, that we have the right matching and thus the right SWR. Yeah, and all what we need is here a second coil, which is called L2. And you guys may know that we can transform an impedance. so it is possible to transform over a transformer. We can transform from a high impedance down to a lower impedance, and of course in our case it is 50 ohm. Okay, so we only need to have a second coil to convert 2.5 kilo ohm down to 50 ohm, and that is then what we need to do to plug here our antenna right to our antenna connector of our TRX. So that is all we need to consider. Okay, and this little additional coil leads us to our impedance transformation, because remember, 2.5 kilo ohm down to 50 ohm, and that is what we want to look into, how we can do that. And how can we express our impedance transformation in a formula? And well, if we see U as transformation factor, right? So we can use our L1 to L2. But finally, we do not really know what is L1 to L2. But what we can say is the windings from 1 to what the turns will be on L2. So that is what we can use as well. And from the given formula for impedance transformation, we know that if we look onto the turns for L1 and the turns for L2, that is equal to the square root out of RA over RI. And RA is simply here the output. L1 is RA, which always watched from our transceiver, so that is the output impedance, and the input impedance here is our RI, which is of course our inner resistor of our TRX. Okay, so that is what is meant here. So we can really say that the square root out of RA over RI, which is here our 50 ohm, and RA is 2.5 kilo ohm. So we can say, seeing this here, it is equal to the square root out of 2.5 kilo ohm over 50 ohm. Okay, and that finally means, if we calculate this here, and again I can put it in the same manner into my calculator as I have it here on my piece of paper, and now I can press my equal button, and you see our conversion factor is 7. Okay, 7 is our conversion factor, so you can see it here. So that simply means that our R inner resistor, so our RI, our 50 ohm side of our transformer, is so the turns on our L2 is 7 times smaller than what we have as turns on our L1, right? So again, here's our L1, and that is our output impedance, and that means that the turns on our outside resistance is 10 times higher than what we have on our input side or on our inner resistor side. So 7. So that is what we really need to remember later when we start to build finally here our inductor. And guys, really don't let yourself get confused by all of this. When you have done it once for yourself, then it really gets clear, because you really need only to follow here the instructions, and you will always get to the right conclusion, to the right values you simply need. Now our next step is, of course, so we found that our L1, which is the outer impedance of our coil, not the outer impedance, the outer inductor, has to be so that is what we found here. L1 needs to be 228 nanohenry, and that is now our next step. We need to build an inductor and transformer which will have on the L1 side 228 nanohenry. Okay, so let's go for that. But before we go ahead, let me simplify our circuit diagram a little bit. So we have seen, when I go back here to our first side, we have seen that we really have two sides of the transformer, which is sometimes not so easy, and therefore let's change over to the auto transformer design, which is what you can see here. So we only have one coil, and we know that we have here on the L1 side an impedance, and we have on the L2 an impedance, and we can pick really our L2 simply by picking here one of our turns. So we simply solder our coax wire simply to the coil, and then it will work as well. So the whole is L1, and where we pick here our L2, so that is L2, and therefore that is much easier than really to have a second winding which we have seen on the other design. So that is much easier, right? Well, and as we said earlier, so we need to wind finally here out of our silver wire our coil. And yeah, so we know that we need our 228 nanohenry. And now, yeah, how can we wind it? I mean, we need an idea how that works, and yeah, that will be now our next step, to find how to do it. And a very easy idea is to take here a normal drill, and you start here winding it something like this here onto a drill, and yeah, we need some turns and whatnot to get finally a coil, but we do not know where we ends up, because remember, once again, we need 228 nanohenry, and that is our goal, and therefore we need a little more mass. Right, so the idea is, as we have seen it here, so we want to put some turns onto a drill, right? So yeah, the black here is, if you like, our drill, and the red are our coil, which we have winded, right? And therefore the drill has a diameter which is D, and then our coil will get finally a length which is called LM. And now we have two figures, the D and the LM, and we need the number for the turns to get finally our needed 228 nanohenry. Alright, and therefore we have this equation here, and well, you see L for our inductivity, and now it is here a little trick, so we put 1 nanohenry here into our formula simply to be able to use all in millimeters, because otherwise we would do it in meters to get to the right result. And sorry for all my friends in the US, so these formulas work with meters or millimeters, so unfortunately you have to convert it. But I believe, I'm not 100% sure, but I believe the formulas you are using over in the US uses also meters or millimeters, so I'm not 100% sure, but there are nice conversion programs on Google, so it shouldn't be that much complicated to convert, if needed, the millimeters into the inches or what have we. Anyways, so what we have here is n squared are finally the turns, and d is the diameter of the inner coil, which we get out when we turn it on a drill. So the inner diameter will be 8 millimeters in this case, because this is an 8 millimeter drill, and then our LM will be at least how long our coil needs to be. So that is what we really need to find out. All right, and the next step is a little bit try and error and a little bit experience. The first what we really can fix is the turns we should try out first, and I have chosen 14 turns here, and the answer why is relatively easy. Remember, so we have determined a transformation factor which was 7, and we need a figure for L1, so 14 turns for instance, which can be divided by 7, because if we look back here to our impedance transformation, we found that the transformation factor is 7. And that is what I've tried to explain you before. And now it might become a little bit easier to understand. When we really have 14 turns, which we wind here around our drill, right? We definitely will get here our possibility to divide it by 7, and then we know we pick here our L2 after 2 windings, right? I mean, it all depends a little bit if it is really 2.5 kilo ohm that Z1, or is it 2.5, or is it 2 kilo? So that is all a little bit theory, but we need a starting point. I mean, at least we have to experiment and to optimize it a little bit to the real conditions. And the real conditions are always a little bit different to what we are calculating here. But that is where we need to start, and therefore 14 turns is excellent. And then it is important to remember we really have a very low inductance, and therefore not too many turns, because as more turns we have, as higher our inductor will be in nanohenry, right? Well, and 8 is simple because I have a drill which is 8 millimeter, and right, then our 55, not meter, so that is of course wrong, it is millimeter squared. And that is where you need here a little bit try back and forth, take 40, take 30, take 60, and then you see where you end up. Maybe you have to adjust here a little bit the drill, so maybe 7.5. So that is a little bit try and error, but finally you will come very close to what you need, so very close to what we have calculated before. And again, I put exactly here into the calculator what we have here on our piece of paper, and let me press the equal button, and what you see, yeah, it is 10 exponent minus 7, which is not so well known in the engineer's world. So we press our engineer button, and you see it is 228 times 10 exponent minus 9. Minus 9 means nanohenry. So let me put it down here. So that is 228 nanohenry if we build our coil like this here, right? And back to what we have calculated before, and it is too nice to be true, because that happens not very often, that you exactly meet the required 228 nanohenry, but that is finally what we got out of this formula. So we ended up with 228 nanohenry, and in theory our construction here should end up with 228 nanohenry. Well, to be honest, I really don't believe it, because that is theory, and if we wind it, then it is all a little bit different. But that doesn't matter at least, because I mean, we always have to deal with little with little differences. That is normal, and that is known. That we really meet this nanohenries is, as I already said, very, very seldom. So if here would now stand to 240 or 190, or I don't know, that would be fine as well. That we exactly meet our requirements. That is too nice to be true. But anyways, now the game is to turn it here on the drill, like so, and so that needs to be 14. So what was it? 14. Yeah, 14 turns. So let me finish it to 14, and then let's see if we really met the right value. Right, so that is our coil, and as I told you, we need 55 millimeter in length, so that is where we need to go up. So I need to do it a little bit more nice at the end, but yeah, just that you get the idea what I meant. So yeah, approximately 55, so you can see it here. I mean, the fine adjustment we do when the construction is completely ready, and that coil here should now yeah, have approximately 228 nanohenry. So let's try it out. Right, and here is our coil connected to our LCR meter, and you see that we are meeting 257 nanohenry, and of course we can here change it a little bit by simply pulling it out a little bit. So you see I've just pulled here a little bit, and you see it is going back and forth. So that depends now on how it will be fixed at the end. And you see now 221. So that is very, very close to what we have calculated, and we can be fully satisfied with you know, the result of what we have here. Yeah, and again here our 228, and you have really seen what we have achieved. So that means finally our coil is already very nice. So what we still don't know is if we are really dealing with 2.5 kilo ohm as wire or antenna input impedance. So that can vary. So that is what we already discussed. So therefore what we need to do by now is simply to build here our little coil, which really needs to go here to our coil. And then, as I already told you, we connect finally our coax cable here at 2 or 3, so that depends on the reality, to our coil here, and that is then in our auto transformer design our 14:2, which is our transformation factor 7, which we have seen before. So we wire it here, so we solder it directly here onto a winding, and then together with our little variable capacitor, it will then work together with our antenna. And have a look. Here is our quick and dirty result. I show you the antenna in a minute. I just wanted to show you that that here is the SWR, and you see that we are at 1.45 for our SWR at 149, and we built, or we calculated our antenna for 149 megahertz, and you see, considering that we can go to an SWR of 2 on both sides, so you see from 145 up to 154, so that is a bandwidth of 8.7 megahertz. We can use this antenna, and quick and dirty, because we can improve here this SWR simply by changing a little bit where we have set our transformer point, so our L2, so we can vary it a little bit to get it better. But you see, finally what we have done is working perfectly, right? So that antenna can directly put into a tree in the field, and you can use it here especially for our Freenet friends who are working on 149 megahertz, so the 2 meter bands, 6 channels, which are free, so you do not need a license for that, and therefore that is what you can put into the tree and you can work. So that is excellent, and once again, you can really do it for any band, so just follow the instructions, right? And here is the design. So as I told you, so we simply put the 3 components together. Here our coil, which we have done. Here is our little capacitor, which we put into it, right? And what you see here, so that is our coax cable, and you see that we picked here a winding where we have calculated, right? And there is our little box for our mini vector network analyzer to analyze it. So we have seen it, it is over there. So there is our diagram, okay, and down there that is our little mini vector network analyzer, and again I have to find it here. Where is it? There is our design, and that's all. And here the wire is going up to the ceiling. I've simply picked it here to the ceiling. I can't get there. Unbelievable. Anyways, I hope you can believe that. So that easy it is, and you definitely do not need finally a vector network analyzer, so you can use your normal SWR watt meter. And what I really need to tell you additionally, so for our half wavelengths, we have chosen here the wire, which is 1 meter long, and when you start fine-tuning it, I mean, yeah, you have to fine-tune it here a little bit, and with you know, here our little potentiometer, or capacity, or variable capacity, and you have to do here, let me see if I can get it better in, so you have to check it here a little bit where you put your wire for the transformation, right? And you see I'm here on the third, I believe. And you know, that is what you need to try. I have also changed it over, because remember, our assumption of 2.5 kilo ohm is not always right, and therefore you have to convert it. Anyways, so all what I have to say is you have to experiment a little bit with it to get it into specs, but it will work fine. So no doubt it is fun. Huh? That is what ham radio is all about. It is just experimenting a little bit until you have the design in a way that it is working as you want to have it, right? And again, here our antenna itself, which is finally the wire here, when you start, you do it a little bit longer than the 1 meter we have calculated, because then when you do your fine-tuning, you can go and you see where, you know, your graph is or your SWR is, and then if it is longer, it needs to be longer as what it was calculated before, and then you can cut it down in really little steps until your tester is telling you now it is fine and exactly there where it needs to be. So therefore longer, and then cut it down in very little steps to come to the needed final length of here our wire. Your coil and your capacitor can be put in little boxes like this here, so that is then as well a little yeah, that is a little shielding, so that what you have fine-tuned and adjusted will finally stay where you need it. Okay, so that is a good idea to do it that way. So there are boxes like this on the market, so that is a Teco box where you all can put it in, so that is very handy. And as promised here, the figures we need for 11 meter 27 megahertz antenna, so half lambda. So we need a wire which is 5.5 meter long, right? So the wire itself should have approximately 1 millimeter in diameter, and then we need here an L, and we need here you know, a little capacitor which is turnable from 20 to 60 PF. Our L should have 13 turns, and we pick at 2 turns here our 50 ohm transformation. So the D, the inner D, so a 15 millimeter drill, and the LM will be 40 millimeter of our coil. Okay, so you can put here a second variable capacitor, also 20 to 60, so that is if you don't want to cut your antenna, because simply you can adjust with this then the lengths, so that will help. If you do not want to cut it, then you need to do it exactly 5.5, and if that is a little bit too long, you can adjust it here a little bit, but maybe the idea to cut it is definitely better, so put it 5.6, leave this second capacitor out, and then easily cut it down a little bit until you get the right figures on your SWR meter. Alright, so that is it for today. Your self-designed mobile ham radio antenna for field purposes or traveling. Hope you learned something and catch you next time. Bye.